This is Richard Gibson. In this video, I'll be providing some background to help understand the data that is recorded by distributed acoustic sensing during a hydraulic fracturing project. Typical DAS datasets recorded during these efforts have a wealth of information related to the developing fracture systems. Today, we'll start by looking briefly at an example of a very low frequency signal extracted from DAS monitoring of a hydraulic fracturing project. Then we'll use a simple model of a small tensile fracture to explain some of the most important features in that data set. The data I'm showing today come from the Hydraulic Fracturing Test Site 2 project, and I'll include a link to some of this freely available data in the video description. To start, I'm showing here a map view display of well geometries. The pink line shows the trajectory of well 4H, and that's the well where the hydraulic fracturing treatment was being carried out. The greenish curve shows the trajectory of well 3H, the well that had the fiber optic cable. The red square shows the location of perforation clusters used for fracturing in this stage, and the red arrows show more or less the path of the developing hydraulic fracture system. Here, we see the low frequency DAS and the heat map. This is the data extracted with frequencies under about 1 Hertz. It includes about 1.5 hours of data, and the middle panel has the slurry rate values during treatment, and the bottom panel shows pressures. Now, we see in this heat map that there are red samples and there are blue samples. Red corresponds to positive strains or lengthening of the fiber optic cable. Blue is negative strains or shortening of the fiber optic cable. Now remember that the fracture system did intersect well 3H with its fiber at a certain point in time and at a certain measured depth. Here, the pink arrows relate those two events. So we see in the map view where the intersection takes place, and in the data view, we see the measured depth, about 18,700 feet, and the time point when that intersection or hit took place. For today, we will focus on the data in this black box. This is the time range before the hit takes place. So that represents behaviors while the fracture system is still approaching and some distance away from well 3H. The red signal that you can see in that box is often described as the heart-shaped signal, because if you turn your head sideways to the left, it does look something kind of like a heart from Valentine's Day. In addition, the signal is slightly bluish or negative at the measured depths above and below that heart-shaped signal. You can see it a little bit more clearly as we approach the time of that fracture hit. Now, it's this data within the black box then that we're going to try to explain in this tutorial today. Specifically, to get started, we're going to take a simple elementary model of a fracture that we can use to build some important intuitions. A couple points to keep in mind. First, DAS measures a component of strain parallel to the fiber optic cable, essentially the lengthening or shortening of that fiber optic cable. That's what we need to evaluate to compare to data. However, it's easier to visualize displacement vectors showing the motion of the rock medium, so that's what we're going to start with before we head to the strain values. Here, I'm showing a detailed 3D perspective view of my simple hypothetical fracture model. It's a small square vertical fracture 1 meter on a side. It's oriented in the north-south direction, and the red arrows show the sense of motion of the rock on each side of the fracture surface. Here, I add a map view of exactly the same model and add a blue line to remind us that it's perpendicular to the well. Now, the other question then is just to make sure we're exactly clear of what I mean by a tensile fracture. So if we take this picture on the right as showing the starting configuration of the fracture, after we pressurize the well and start inducing the hydraulic fracture, the two sides of the fracture will move away from each other and add some non-zero value of aperture on that fracture. Now, I'm not going to show the math, but using some standard solutions, we can take this simple model and compute the motion of the rock medium around that fracture. This motion or displacement of the rock is easy to visualize using the arrows in this plot, which show the motion at the depth of the fracture. The first important thing to see is that the lengths of the vectors decrease very quickly away from the location of the fracture. This tells us that signal levels rapidly increase when the fracture gets closer and closer to the sensor. This is our first important conclusion. It does make the plot a little bit cluttered though, so I'll replot these vectors by rescaling their lengths to make it easier to see. So this plot here now shows exactly the same results, except that I've adjusted the lengths of the vectors to clarify the information a little bit, make it a little bit easier to detect patterns. We can still see that they are longer close to the fracture, but we can focus more clearly on the orientations or directions of ground motion. So if we start by looking to the right of the fracture here, the fracture surface pushes to the right, and the motion is exactly to the right. The opposite is true on the other side of the fracture, where the fracture surface pushes to the left. Now, as we start to look at other locations with different orientations with respect to the fracture, the directions of the vectors gradually changes. And then when we're exactly south or north of the fracture, we see that the medium is pulled inwards towards the fracture, the opposite of the trend we saw on the left and right of the fracture surface. If our fiber optic cable, that is, measured displacement or motion, we'd be done. For better or worse, though, DAS measures strain, so we need to take another step or two to see what type of DAS signal will be generated by this same fracture model. To do this, I'll include a hypothetical fiber optic cable location at a north-south coordinate 30 meters above the fracture. This cable will measure the strain in the direction of the blue line, or the rate of change of displacement in that direction. So the next step is to focus in on just the horizontal east-west component of displacements at that fiber location. That's exactly what I'm showing in this illustration here. So if we look on the left, we see that the vector, the component of horizontal motion, points to the left. That's a negative displacement. It gradually approaches zero, and then it reverses direction and becomes positive on the right side of the fracture here. Here, I present a simple plot of the value of this component that we just were looking at with arrows, and I'm showing it in terms of the curve that shows the displacement now with an east-west coordinate range of about minus 150 to 150 meters. We see again that the values are negative for locations left of zero and positive to the right. The strain measured by this model fiber optic cable is just the derivative or slope of this curve, and the result is a simple symmetric strain curve that has two local maxima or peaks right here. There are also zero strain values, which correspond to the locations of the local minima and maxima in the displacement plot. We can also ask what happens as the distance between the fracture and the cable decreases. We already know that the displacement amplitude will increase a lot, but what about the strain? These results show us that the strain signal also increases dramatically. The solid curves are the same as the ones I just showed you, but the dashed lines now show the results if the fracture is only 10 meters away from the DAS cable instead of 30 meters. Very importantly, the shape of the strain curves is still essentially the same. It still has these two peaks that we see right here. But because the fracture is now closer to the fiber optic cable, the distance separating these two peaks is decreasing than in the earlier case. So if we make the fracture draw closer and closer to the fiber optic cable, those two peaks will gradually combine or coalesce, exactly as we saw in the data. So here again, I show the low frequency DAS data we started with, and I also plot one of the model results, except rotated on its side compared to the previous two displays. Looking at the data at the time point illustrated by this green line, we see that the trends are the same as we have in the model curve. Slightly negative values, two peaks, and again, slightly negative values. Negative, peak 1, peak 2, and negative. And if we add a couple more lines to emphasize the positions of these peaks, we know that as the fracture draws closer and closer to the fiber optic cable until this time of the fracture hit, those two peaks get closer and closer together. Again, just like we saw in our model predictions. To summarize, we use this very simple toy model to develop some very powerful insights into low-frequency DAS data. We can explain the two peaks or lobes in the so-called heart-shaped signal, and we explain the dramatic increases in signal amplitude as the fracture gets closer and closer to our monitoring fiber optic cable. The next video will expand on this model and start to make it even more complete to help understand more and more completely our low-frequency DAS data. Thanks for watching.